Okay, now let's look at if our molecules are polar or non-polar. The nice thing is this section is relatively short. We're going to extend it out because we're going to go through quite a few examples. Okay, recall from previous videos about bond polarity. Remember, if the two atoms in your bond have different electronegativity values, if their electronegativity values are different, that bond is polar. But the question is the entire molecule polar? Does the entire molecule have a dipole moment where one end of the molecule has a partial negative charge and the other end of the molecule has a partial positive charge? The way we figure this out is by adding up all of the individual dipole moments and seeing if they cancel each other out. If they do, if all the dipole moments cancel each other out, then there is no polarity to your molecule. It's a non-polar molecule. If they don't all cancel each other out, if you see, oh, you look at all these individual dipole moments, but they aren't canceling, then no, they don't cancel each other out, then it is a polar molecule. It's pretty much that straightforward. Do they cancel each other out or not? So let's go back a page and let's look at some of these shapes that we've already done, some of these molecules we've already looked at, but now let's see if they're polar or not. And note, when people say chemistry is tough, what they really mean is, man, it can get complicated. Because let's think about the question. One simple question. Is this molecule polar? There's only two possible answers, yes or no. Yes, it is polar. No, it is not polar. But how do you decide whether it's polar or not? I mean, heck, you got a 50-50 chance of being right just by guessing, but how do you make sure you get the correct answer if it's polar or not? What do you have to do? Well, to determine if it's polar or not, the first thing you need to do is you need to draw the Lewis structure. So you need to count all the electrons, follow all the rules, draw its Lewis structure. Once you have its Lewis structure, you need to put it in the proper geometry. So you have to remember all of your geometries. Once it's in the right geometry, you then have to remember the dipole moments. Look, all the bond dipoles, write them down. And then once you have that, you have to see if they cancel each other out. And once you've done all that, you can finally answer the question, is this molecule polar, yes or no? So that's a lot of work for a yes or no question, but that's what it takes. So, since we've already done the Lewis structure and the geometry for these molecules, let's just go straight to the beast, see if it's polar or not. BeCl2. Well, note, it's 180 degrees. What is more electronegative, chlorine or Be, beryllium? Well, we know chlorine's more electronegative, so we know this bond is polar, and we draw the dipole moment like that. This bond is polar, this boron, or the beryllium-chlorine bond is polar. Note how those two arrows are in opposite directions. That means they cancel each other out. Arrows in opposite directions cancel each other out. So this molecule is non-polar. They cancel each other out. What about CO2? Well, oxygen's more electronegative than carbon, so this bond is polar in that direction, but this bond is polar in that direction. Note, those two arrows cancel each other out. CO2 is also non-polar. BF3, things look a little tricky here. They kind of are, but I'm gonna, after we're done with it, I'll give you a little hint. When we look at BF3, we know that fluorine is the most electronegative element, so it's definitely more electronegative than boron. So this has a dipole moment here. This boron-fluorine bond has a dipole moment here. And this boron-fluorine bond has a dipole moment here. The question, do these three dipole moments cancel each other out? In fact, they do. If you've had vector algebra or vector addition, basically you're adding this vector plus this vector plus this vector. And what we find is this one going down this way to the left and this one going down this way to the right. Those two add up to be a vector going straight down this direction, which is canceled out by this vector going straight up in that direction. So, yeah, these three are going to actually cancel each other out. A little bit of a hint. If your electronic geometry and your molecular geometry are the same, and all of your terminal atoms are the same, then the molecule is nonpolar. All of the vectors, all of the dipole moments cancel each other out. Note, this is a boron with 3 fluorines, so all of our terminal atoms are the same. This is trigonal planar electronic geometry because there's no lone pairs on the boron. Since there's no lone pairs, the electronic geometry and the molecular geometry are the same, both trigonal planar. Therefore, it'll be a nonpolar molecule. They will cancel each other out. Now let's look at NO2. And the best thing about polarity, since we know all the ins and outs and whatnots of resonance structures, we know that neither one of these are right, that both these bonds are the same. They're not single bonds, they're not double bonds, they're somewhere in between. We know oxygen is more electronegative than nitrogen. Doesn't matter which resonance structure we do. And your first thought would be, oh, wait a minute, do these two cancel each other out? The answer is, uh-oh, crud. This is the Lewis structure. This is not the geometry. So we can't do it just on the Lewis structure alone. We need to do it on our drawing in the proper geometry. Note that NO2- is bent. So we have to look at this molecule here and question, do these two arrows cancel each other out? The answer is no, because they are not going in exact opposite directions. This one's going down this way. This one's going down this way. These two vectors would actually add up to a vector like that, going down this way. So this molecule is polar, because the dipoles do not cancel each other out. And note, we could expect that because the electronic geometry was trigonal planar, the molecular geometry was bent. These two are different geometries. There's a good chance it's going to be polar. Unfortunately, we will find out later on that doesn't always work, but if your the one thing for sure, if your electronic geometry and your molecular geometry are the same, it is definitely polar. If the electronic geometry and molecular geometry are different, then you really still need to work it out. All right, let's look at CH4, this tetrahedral molecule down here. First of all, we know that hydrogen and carbon have very similar electronegativity values, but hydrogen's just a little less electronegative. So we've got little, and I'm going to draw small little arrows, little dipole moments going this way. We know this is tetrahedral. Do all of these arrows cancel each other out in a tetrahedron? Well, it turns out if you've got this arrow going this way, this one going this way, this one going this way, and then one going down, all 4 of those arrows actually do cancel each other out. Note, the molecular geometry and the electronic geometry are the same. They're both tetrahedral, so this is nonpolar. All of the dipole moments cancel out. All right. Let's go on to the next page. Cl3, polar or nonpolar? Well, yeah, let's make sure we don't make a mistake. Make sure we actually use the drawing in its proper geometric form. Note, chlorine is more electronegative than nitrogen. Ooh, well, chlorine, nitrogen? Yeah. Chlorine, nitrogen are actually very similar in their electronegativity values. The good news is we don't have to know exactly what the electronegativity values are. Chlorine's a little bit larger. I do believe nitrogen's just a hair more electronegative than chlorine. Don't know for sure, so I'm not going to worry about it. But the thing to note is, no matter which way these arrows are going for this molecule, we've got this lone pair up here. What do we do with our lone pairs? The best idea is just to ignore them. If you're actually calculating the dipole moments of the molecules, you need to consider that lone pair. But if the question is simply if it's polar or nonpolar, just ignore lone pairs there. So the question, do these three arrows cancel each other out? Well, they don't, because they're not in a trigonal plane. They're all three arrows have this up component to them. There's no arrow here going down, so these three do not cancel each other out. This is polar. Water. Well, oxygen definitely more electronegative than hydrogen. So we've got these two arrows here. They do not cancel each other out because they're not straight. There's only two of them. They're not straight across. Water, definitely polar. Note I just ignored the lone pairs for this discussion of polar versus nonpolar. All right. Now this looks super complicated with PCl5, but is there a hint here that says that this is actually easier if we're determining if it's polar or nonpolar? Yeah, this is trigonal bipyramidal molecular geometry. There's no lone pairs on the phosphorus, so it's also trigonal bipyramidal electronic geometry. Therefore, it is nonpolar because the electronic geometry and the molecular geometry are the same. Yeah, it turns out the chlorine is more electronegative than phosphorus, so this arrow going up here will be completely canceled by the arrow going down here. So all that's left is these three arrows, but we already determined earlier that if it's trigonal planar and the same atom, all three of those arrows do cancel each other out. So this one's canceled out by this one, and these three dipole moments all cancel themselves out. Nonpolar. Oh, what about this one down here, SF4? Well, fluorine is more electronegative. So we've got these two arrows. Note, this arrow and this one cancel each other out. But what about these two? Does this one here cancel out this one here? No, they don't. Because these three positions are in a trigonal plane, in order for these two to be canceled out by this one, this would have to be a fluorine over here. Since there's not a fluorine over there, it's a lone pair, which we're going to ignore. These two arrows are not canceled out, so this is polar. Running through these a little quick, we can see, okay, we've got an arrow here, an arrow here. Those two cancel each other out. This one is not canceled out by those lone pairs, so this is also polar. And, whoop. No lone pairs on that central sulfur, so it's octahedral electronic geometry, octahedral molecular geometry. It is nonpolar. Although it's a bit of work, you can see that this arrow is canceled by this one. This up arrow would be canceled by a down dipole moment. This right dipole moment canceled by the left dipole moment. So that would also be nonpolar. The concept of polarity is actually pretty darn important. Your book mentions it real briefly, so I'll mention it briefly here. It turns out when you're looking at what molecules will dissolve in what other molecules, what solutes dissolve in what solvents, the general rule is polar things like other polar things. So polar solutes will dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. So water is very polar. Water is quite polar, and so other polar things will dissolve in water. Oil is a nonpolar molecule. The oil molecules are not polar, and so oil nonpolar molecules do not dissolve in water because nonpolar things like oil don't dissolve in polar things like water. Salt, sodium chloride, is like the most extreme of polarity. It's so dang polar, it's ionic. So NaCl, sodium chloride, is so polar, it's so ionic, or it's ionic, so it's like extremely polar. So salt does dissolve in water because water is also polar. All right, so that will conclude our drawing of our structures at this point, because now we have a bit of an issue, and this is going to be a little bit complicated for you right now. Guaranteed, once you're in organic chemistry in 2 semesters, this is going to be easy for you. But right now, it's going to be a little bit difficult, so we need to go through our next issue a little more slowly, valence bond theory.